There is an image sitting in NASA's servers right now that should not exist. Not because it was difficult to take, not because the technology was not ready, but because what is in the image contradicts something we have spent decades being confident about. It shows galaxies that are too bright, too massive, too chemically complex, and too organized to exist at the moment in cosmic history when they were photographed. And yet, there they are, fully formed, blazing with light, in a universe that, according to our best models, had barely had time to produce anything at all. The James Webb Space Telescope has been photographing the beginning of time, and what it has found there is quietly breaking physics. Tonight we are going to tell the full story, not just what JWST is and how it works, but what it was built to find, what it actually found instead, and why the gap between those two things is one of the most significant unsolved problems in modern cosmology. Let us start with light. Light travels at a fixed speed, 300,000 kilometers per second, always, everywhere, without exception. That speed is one of the most fundamental constants in physics, and nothing in the universe violates it. But it has a consequence that is easy to understand and almost impossible to fully absorb emotionally. When you look at something far away, you are not seeing it as it is now. You are seeing it as it was when the light left it. When you look at the sun, you are seeing it as it was 8 minutes ago. When you look at the nearest star beyond our solar system, you are seeing it as it was 4 years ago. When you look at the Andromeda Galaxy with the naked eye, you are seeing it as it was 2.5 million years ago, before our species existed, before any member of the genus Homo had taken a single step on this planet. And when the James Webb Space Telescope points at the deepest, most distant regions of the observable universe, it is looking at light that has been traveling for over 13 billion years. It is not looking across space, it is looking across time. The telescope is a time machine, and the further it looks, the further back it goes, all the way to the universe's earliest moments. This is not a metaphor. The light in JWST's images left its sources when the universe was a few 100 million years old. The universe is currently 13.8 billion years old. Those photons have been traveling for longer than the Earth has existed, longer than the sun has burned, crossing an expanding universe that has stretched the very space they were moving through, arriving at a mirror the size of a tennis court, orbiting the sun 1.5 million kilometers from Earth, and being focused into an image that humans can look at and call a photograph of the beginning of time. That is what JWST does. Now here is why it matters so much that we built it. Before JWST, our picture of the early universe was constructed from theory and from the limited observations of Hubble, its predecessor. And from that picture, we developed a model. The Lambda CDM model, which stands for Lambda Cold Dark Matter, is the standard model of cosmology. It describes how the universe began, how it expanded, how matter clumped together under gravity, and how that clumping eventually produced the structures we see today. Galaxies, galaxy clusters, the cosmic web of filaments and voids that organizes matter at the largest scales. The model made specific predictions about what the early universe should look like. It predicted that the very first galaxies would be small, dim, chemically primitive. The universe had only just produced its first stars, and those first stars had only just begun the process of fusing hydrogen into heavier elements. Carbon, oxygen, nitrogen, iron, the chemistry of complexity, takes generations of stars living and dying to accumulate. The first galaxies should be made almost entirely of hydrogen and helium, the only elements that existed in significant quantities after the Big Bang. They should be irregular and chaotic and faint, building blocks rather than finished structures. That is what we expected to find. That is not what we found. In January 2026, NASA confirmed the detection of a galaxy called MOM-Z14. It existed 280 million years after the Big Bang. To put that in context, the universe is 13.8 billion years old. 280 million years is 2% of that age. MOM-Z14 is a photograph of the universe in its absolute infancy. And what JWST found there was not a small, dim, primitive building block. It was a galaxy that was already bright, already compact, already chemically enriched with elements that should have required multiple generations of stars to produce. The lead researcher described it simply: the early universe looks nothing like what we predicted. And MOM-Z14 is not alone. JWST has been finding these unexpectedly luminous early galaxies consistently and repeatedly across multiple surveys and programs. One of the largest is Cosmos Webb, a project that awarded the telescope over 200 hours of observation time, the most allocated to any single program in JWST's inaugural year. Cosmos Webb captured a panorama of cosmic history showing galaxies across 9 different epochs of time, and in the earliest epochs, it found 10 times more galaxies than astronomers had anticipated. Not a small discrepancy, not a rounding error. 10 times. An order of magnitude more galaxies than the standard model predicted should exist in that era. There is a phrase astronomers keep using when they describe what JWST is finding. They say the universe was in a hurry to grow up. One researcher studying an early galaxy cluster put it this way: the evidence suggests the universe grew up faster than it should have been able to. Another team studying a galaxy that existed just 800 million years after the Big Bang found a supermassive black hole at its center that was already far too massive for its host galaxy. Under the standard model, galaxies form first and gradually grow black holes in their cores, the two structures developing in lockstep over billions of years. This galaxy's black hole had gotten ahead, dramatically ahead, in a way the model cannot explain. To understand why this is so alarming, you need to understand what a model in cosmology actually is. The Lambda-CDM model is not a rough sketch or a preliminary guess. It is one of the most precisely tested and observationally supported frameworks in the history of science. It correctly predicts the large-scale structure of the universe, the distribution of galaxies across billions of light years, the temperature fluctuations in the cosmic microwave background, the abundance of light elements produced in the Big Bang. It has been tested against observation after observation for decades, and it has passed every test. It is the kind of model that physicists stake careers on, that textbooks are written around, that entire research programs are built to extend rather than to question. And JWST is finding things it cannot account for. The specific problem is called the galaxy luminosity function problem, though that name undersells what is actually going on. The standard model predicts how many galaxies of a given brightness should exist at each stage of cosmic history. It predicts fewer and dimmer galaxies in the early universe and more and brighter ones as time goes on. JWST is finding that in the earliest epochs, the galaxies are far too bright and far too numerous. The model's predictions and the telescope's observations do not match. Something was producing stars and galaxies faster in the early universe than our physics says should have been possible. 3 possible explanations are currently on the table in the research community, and none of them is comfortable. The first is that our understanding of early star formation is wrong. The first stars may have been far more massive than we assumed, burning brighter and hotter and dying faster, producing heavy elements and ionizing radiation on timescales our models did not account for. If the first generation of stars was dramatically different from anything that exists today, the rapid chemical enrichment and brightness of early galaxies becomes more explicable. But it requires revising something fundamental about how we think stars form from the primordial gas of the early universe. The second explanation is that early galaxies were simply more efficient at converting gas into stars than galaxies are today. Modern galaxies are relatively inefficient star-forming engines. A significant fraction of available gas never becomes stars, either blown out by stellar winds and supernova explosions or kept hot by the radiation of active galactic nuclei. Now, if early galaxies were forming stars from nearly all their available gas rather than the small fraction modern galaxies use, their brightness and mass would be more consistent with what JWST is seeing. But again, this requires explaining why the physics of star formation was so different in the early universe. The third explanation is the most uncomfortable of all. There is a small but growing number of cosmologists who argue that the discrepancy is severe enough that it cannot be solved by adjusting parameters within the existing model. That, what JWST is finding, points to a genuine gap in lambda CDM itself. That our understanding of dark matter or dark energy or the initial conditions of the Big Bang is incomplete in ways that become apparent only when you look at the universe in its earliest moments. The standard model has never been tested at this extreme. Every previous confirmation of it has come from observations of a universe that was already hundreds of millions of years old. JWST is reaching into the gap where the model has never been directly verified, and the gap is not empty. There is one more piece of this story that does not get enough attention. JWST is not just photographing distant galaxies. In March 2025, NASA revealed that a galaxy called JADES-GS-Z 13-1, observed just 330 million years after the Big Bang, was emitting a specific kind of light called Lyman alpha emission. This is light produced by hydrogen atoms that have been ionized and are recombining. Under the standard model of early universe physics, this should have been impossible. The early universe was filled with a dense fog of neutral hydrogen gas that absorbed this type of light completely. Scientists called this era the epoch of reionization, the period before enough stars had formed to ionize the surrounding hydrogen and clear the fog. The standard timeline places the clearing of this fog at a specific point in cosmic history, well after the moment when JADES-GS-Z13-1 was observed. The galaxy was emitting light that should have been absorbed. The fog should have been blocking it, and yet the light was getting through. One possibility is that the galaxy had somehow already cleared a bubble of ionized space around itself, a local region where the fog had been driven away by the energy of its own stellar radiation. But the scale of clearing required to explain the observation challenges current models of how quickly early galaxies could have ionized their surroundings. It suggests the process of reionization may have begun earlier and proceeded faster than the standard timeline predicts, which connects back to everything else JWST is finding. An early universe that was doing things it should not have been able to do yet. On timescales, the model says we're too short. What does any of this mean for the future of cosmology? It does not mean the lambda CDM model is wrong in its entirety. It means it is incomplete. The most likely outcome is not that decades of cosmological work are discarded, but that they are extended. New physics at the frontier, parameters adjusted, processes accounted for that the model did not previously include. And science has been here before. General relativity did not erase Newtonian mechanics. It extended it, revealed its limits, and explained the cases where it failed. Whatever emerges from the crisis JWST is creating will likely do the same to lambda CDM. But the emergence of that new understanding requires data, more observations, deeper surveys, larger samples. JWST is already working on this. The Cosmos Web survey that revealed 10 times more early galaxies than expected is being followed up with more detailed spectroscopic observations to confirm distances and characterize the chemistry of each galaxy. The Nancy Grace Roman Space Telescope, currently in development, will combine JWST-level infrared sensitivity with a field of view far wider than any current instrument, potentially pushing the sample of these unexpectedly bright early galaxies from dozens into the thousands. And every new data point is a test of whatever model eventually replaces or extends lambda CDM. Every unexpectedly bright galaxy, every supermassive black hole that arrived before its host galaxy, every fog-clearing emission from a universe that should have been opaque is a constraint that the new model must satisfy. There is something worth sitting with at the end of all of this. The James Webb Space Telescope was built to answer questions, to see the first galaxies, to understand how the universe transitioned from the dark, featureless aftermath of the Big Bang into the structured, complex, light-filled cosmos we inhabit today. It was pointed at the beginning of time, and it took photographs that humans are now studying in offices and at desks and in seminars around the world. And what those photographs revealed was not the confirmation of what we expected. They revealed that the beginning of time looks stranger than we thought, that the universe grew up faster than our best models said it should, that something happened in those first few 100 million years that our current physics does not fully account for. That is not a failure. That is science working exactly as it is supposed to. You build the best instrument ever pointed at the cosmos. You look at the places no instrument has ever reached, and you find that the universe is more complicated, more surprising, and more interesting than the model you built without that data. Think about what it took to get here. The James Webb Space Telescope spent 25 years in development. It was delayed, redesigned, over budget, and nearly canceled multiple times. The engineering challenges it required solutions to did not exist when the project began. A mirror that had to fold origami style to fit inside a rocket and then unfold perfectly in the cold of space 1.5 million kilometers from Earth, with no possibility of a repair mission if anything went wrong. A sun shield the size of a tennis court made of a material thinner than a human hair that had to deploy correctly in sequence across dozens of mechanical steps, every single one of which had to work the first time. The telescope launched on Christmas Day 2021, and over the following months unfolded and cooled and calibrated itself without a single critical failure. The engineering margin was so tight that if any one of 344 single-point failure mechanisms had gone wrong, the telescope would have been lost. It did not go wrong. Every single step worked. And the reward for that 25-year investment, for the careers and the funding and the engineering heroics that made it possible, was a photograph of something we did not expect. A beginning of time that breaks our best theory. The photograph exists. The beginning of time has been seen, and it does not look like what we predicted, which means the best part of this story is not the image. It is what comes next. Good night.